What's up guys, today I'm going to be doing a video on the choose function and how it relates to the binomial expansion or just the multinomial expansion in general. So imagine we've got a bag with 6 counters, blue, green, red, purple, yellow, orange, and we want to know how many ways we can choose 3 counters, and note that the order does not matter. So an example we could have is green, purple, orange, but in that case, orange, purple, green would be the same thing, and all other permutations of green, purple, orange would be completely irrelevant. So if we step back for a second, we can try and attempt this problem and say order does matter. That makes it a lot easier. So there's 6 ways of choosing the first counter, and then if I just say I chose blue, there would be 5 ways of choosing the second, and if I say I chose red, then there would just be 4 ways of choosing the next. And another way we can write this, and you'll see in a second why this is useful, is 6 times 4 times 3 times 2 times 1 all over 3 times 2 times 1. And this is just 6 factorial over 3 factorial. And if this was in a general case, in general, we could rewrite this as n factorial, where n is the number of counters in the bag, over n minus r factorial, where r is the number of counters that we want, so in this case 3. So as you can see here, let's say we got the combo green, purple, orange. We would actually get 6 combinations from this, because what we've done is chosen 6, chosen 5, chosen 4, so 6 times 5 times 4. So we've counted the order, but as we said before, we didn't want the order. So in this case, I've just listed them out, which is 6. But if there was a mathematical way to do this, which there is, it would be 3, because there's 3 ways of choosing the first one, times 2 times 1, because there's 2 ways of choosing the second colour, and, well, 1 way of choosing the last one, which is just 3 factorial. So remember, we don't want this. So what we can do is we can get the original formula, which was n factorial over n minus r factorial, and we have 3 as r in this case, so we can then divide the whole thing by r factorial again. So this is the general formula, and what it would be for this question would just be 6 factorial over 3 factorial times 3 factorial. And if you ever get a question where you're asked to do this manually, you'll find out that it's really fast to do, because I'm going to write out the whole thing for the sake of this question. 6 times 5 times 4 times 3 times 2 times 1, and then times 3 factorial twice. So what you'll notice is these are always going to cancel with these. And so now we just have 6 times 5 times 4 over 3 factorial. And at this point, we can just see that there's a 6 on the bottom and a 6 on the top. So this is just 5 times 4, which is 20. Okay, so what we have just used is the choose function. And the way that we write this is n, c, r, where again, n is the number of counters I chose in this case, or it could be a number of anything, and r would be the number of things that we want. It would be n choose r, where n is, in this case, the number of counters in total. It could really be anything, the number of cards, the number of digits for a password. And r is the number of things that we want to choose. So I've written the formula up here, I'll write it down again. N factorial over n minus r factorial multiplied by r factorial. So how does this all relate to binomial? Let's say we've got x plus y all to the power of 6. So I've written down what that would look like here. So we want 4 x's and 2 y's. So if we use the knowledge of the choose function from before, we know that there's 6 brackets to choose from, and we only want to choose 4 x's. So this would be 6 choose 4, and we've chosen 4 x's, so it would be x to the 4. Now let's imagine that I've used 4 of the brackets. So this will just be one of the many permutations. I've chosen that one, I've chosen that one and that one. So I've only got 2 brackets left. And the important thing to note is that there are only 2 brackets left and I need 2 y's, right? I want x to the 4 y squared. So there's only really one way of doing this. But if I use my choose functions from before, I can just say 2 choose 2. And mathematically, you'd figure out this is 1. But just looking at the brackets, we can see that there's only one more way of getting 2 y's. So there's 2 choose 2, or 1 times y squared, because we've got 2 y's. So if we evaluate this, we can use the choose function from before. And this is 6 factorial over 4 factorial times 2 factorial. And there are 4 x's, 2 y's. Get rid of these brackets. So we know that the 4 factorial in the denominator will cancel out with the 4 times 3 times 2 times 1 from the 6 factorial. So what we have left is 6 times 5 divided by 2 factorial, which is just 2. So this is just 6 times 5 over 2, which is 15. So this evaluates as 15 x to the 4 times y squared. So the coefficient of x to the 4 y squared is 15. Okay, so let's say I've got a trinomial now, x plus y plus z all to the power of 4. And again, I've written it down so that there's 4 separate brackets. And let's say that I want 1x, 2 y's, and 1 z. So I've got 4 brackets to choose from, and I want 1x, so that will be 4, choose 1. And again, there's only 1x. And then, let's choose a random bracket to cross off. I want 2 y's, and there's 3 brackets left. So that will be 3, choose 2, times y squared. And again, I've used 2 random brackets. Let me cross this off. And there's only one way of choosing another z. So, again, I'll write it in the form of the choose function, which is 1 choose 1 times z. But we know for a fact that this is just 1, because there's 1 bracket left. So I'm going to evaluate this as 4 factorial over 3 factorial times 1 factorial multiplied by x. And then this is 3 factorial over 2 factorial times 1 factorial times y squared. And then we saw this was 1, so you've got a z. And again, this is the 3 factorial on the bottom is going to cancel out with the 3 times 2 times 1 on the top. So this is just 4 multiplied by, and then I'm going to evaluate this second choose function here. 3 factorial over 2 factorial. That's just 3 times 3. And then we had 1x, we had 2 y's, and 1 z. So this is 12 x to the power of 1 y squared z to the power of 1. So this really works for any, multinomial. It could be 2, 3, 4, doesn't matter.